Thank you so much for having me. It's really great to be back in the CS Ed community. This is where I did my graduate work, and it's always just, it's just wonderful to be in these spaces again. So let's dig in. Imagine, if you will, a talented CS student's transcript at graduation, right? Usually we talk about the beginning and the middle of the process. Let's look at the end. That transcript might look something like this. In the first year, because of previous programming experience, that student was able to skip intro to programming and instead took a broader principles course, giving a sort of overview of major concepts and advancements in programming. Such a course might hit major algorithms like breadth first search, programming styles, functional programming, maybe even logic programming if we're going really old school. Might get into some theory, finite automata, Turing machines, those sorts of things. Next up, you take a data structures course, obviously. That might get you into C++. You get the normal sort of collection of topics there that you would expect, linked lists, binary search trees, maybe hashing. The following year, they take courses in logic for computing, discrete math. Because they're doing pretty well at this point, they can get into a software engineering course by the end of year 2. Along with formal algorithms course to dive into dynamic programming, graph algorithms, all that fun stuff. After those first 2 years, our student gets into project courses. That's kind of the rush to get to the software engineering course. In most schools that have longer term projects, this is going to be a 3rd or 4th year experience, of course. And in a lot of places, it's a single course. It's not unheard of for it to be a full academic year. Or to be waived if you can show a certain level of work in placements or internships or co-ops. Our student might heavily invest in their CS course load and take this project course, operating systems, programming languages, maybe followed by graphics and networks. In their 4th year, they decide they are very interested in systems stuff. They take an elective in advanced operating systems and an independent research project in networking. And they finish off the core requirements with a theory of computation course. And to ensure that they're well-rounded or at least exposed to a lot of CS topics, there are a couple credits for colloquium and the like throughout the 3rd and 4th years. By my count, this student is taking maybe 14 courses on a semester schedule, which I think works out to about 20-ish on a quarterly schedule. And there's a couple of things to note here. We completely skipped a few major topics: databases, compilers, AI or machine learning, computer architecture, distributed systems, parallel and concurrent programming, computer security, HCI. We also skipped or at least glossed over all of the soft skills: technical writing, communication, ethics for technology. Now here's a question for you. When is the date stamp on this student's transcript? I suspect that we could find transcripts that look very much like this going back to the early or mid 90s. And I'm almost positive that you could find transcripts that look like this today. Even with all of those major topics missed. By now, you may have guessed that student was actually me. I filled in a couple of those gaps in grad school with good courses in architecture and AI. And that's also, grad school is also where I learned that my passion is really computer science education and teaching. But all of the other missing topics were things that I either had to pick up on my own: distributed systems, parallel and concurrent programming, security, writing, communication, ethics, and the topics that we did cover as an undergrad. My undergraduate experience, even at a very, very good school, was clearly just a starting point. Nowadays, with that background, I find myself in sort of a niche, weird position at Google, where I've been for almost 12 years now. And I'd like to think that I'm a respected voice in topics of software refactoring, maintenance, testing, API design, software engineering as a discipline. Because of my biases and upbringing and graduate experience, I tend to look at a lot of our productivity concerns or bugs generally through sort of an educational lens, right? The root cause in most problems is education, in my opinion. So that's why I like conferences like this. And so I spend a lot of time internally at Google just answering questions, teaching classes, and writing. Try to put down on paper the common problems and solutions that people are running into that we have learned the hard way too many times, so that we don't need to go through the same pains over and over again. None of that should be all that surprising. I even led the project to write down a lot of those lessons in the big picture form and publish it. That's the Software Engineering at Google book. Hard copies are available from O'Reilly. The material is all freely available online. Neither I nor Google are making any money here. We're really just trying to help. But I bring that up because as a result of that book, for the past year or so, I've also been participating in the ACM, IEEE, AAAI Joint Committee for Computing Curricula, CS202X. We had sessions about that yesterday. And in particular, I'm helping out with the software engineering, intro to programming, and ethics knowledge areas. And so I've been looking at a lot at what our current and proposed future curriculum requirements look like. Also, as a result of the book, I've been focusing a lot of my internal efforts on ongoing education. We're just wrapping up a pilot program where we took a few dozen experienced engineers, the tech leads for their team, and gave them roughly graduate level courses on software design and software testing. These are domains where a lot of wisdom is needed to excel, and where the problem is one of inherent complexity, right? Wisdom and understanding dominate whether you are going to succeed. As a direct result of the CS202X work, I know with some certainty, for instance, that most of our new grad hires have limited experience with, say, automated testing. And that is a daily activity at Google, right? Every change that you are going to make to the code base is going to come with unit tests, right? Period. That is the rule. And I believe that there is very good reason for it to be required where we are and kind of rare and odd as an undergraduate experience, right? And that's primarily because testing is basically a protection against unwanted change and regression. But the amount of time available in a course and the amount of collaboration available in a course means that stuff is not going to change unexpectedly out from under you with that limited amount of time and with the coordination amounts between people, right? You're not regularly running big team projects. And so testing, as an example, comes across, I think, either as a high overhead way to demonstrate that your code works now, which is good, but kind of misses the point because it's really this protection for the future, or it comes across as a kind of a weird and inauthentic way of protecting against things that students haven't experienced, right? It's very hard to teach lessons that don't feel authentic and critical to the experience, to your understanding at the moment. So the result here, I don't feel like I necessarily fit into either camp, right? I'm not exactly an academic, but I'm also a little bit more academically flavored than most of my industry brethren. And so I'm biased by my Google experiences, production systems, and use cases in ways that may not generalize to academia. So I'm kind of falling through the cracks in some ways. But I do hope that one of the upsides of this sort of weird in-between space is that I can maybe help bridge the gap between these two groups. So if you will, here is what I see as sort of the major disconnect between the industry, or at least the super big tech Google style parts, and CS education. And obviously this is all opinion and biased, so pick an appropriately sized grain of salt. But I will start with a critique from my industry leadership colleagues, right? We have got to stop assuming that schools are going to give us graduates with all of the skills that we want, right? Think back to my transcript. I took a pretty significant load that was more than the required amount for a CS grad. Depending on which definitions that you go with, the assumed time commitment for a standard 3-credit course over a semester ranges from about 130 to about 180 hours of engagement. Lecture, labs, reading, assignments, etc. Or put another way, one class is roughly the time commitment of a month of full-time work at a job. I took 14 courses. If you account for vacations, holidays, and some charitable rounding up, robust undergraduate curriculum is about the level of time commitment that you get from a 1.5 years on the job. And the idea in general is that a robust undergraduate program can take non-programmers and give them both the theoretical and practical skills needed to pursue a career in computing, whether that is academic or industry focused. Let me say that again, right? An undergraduate CS program is charitably a 1.5 years of full-time experience, starting from maybe 0 programming. And my industry colleagues are always seeming to believe that that can be the end of formal education and training. That seems wildly optimistic to me. If all of the industry folks are asking you for the impossible, right, point them at this talk, right? Because I do think that they are asking you for the impossible. Consider, which is harder, becoming a fluent programmer or becoming a fluent reader? I asked on Twitter a few weeks back, because that's where all science happens. And I was surprised, I'm joking, obviously. And I was surprised at how weirdly bimodal the results were. I think a ton of this is pinned on our notions of what is fluent. To my mind, just considering the hours of practice and level of concentration required, I think that the two are kind of broadly comparable within a factor of 2 in either direction. Yes, most 6 or 7-year-olds have learned to read, but we all know that they're still practicing and it's still effortful, and it's going to be years of additional practice and instruction before you stop noticing clear gains in reading fluency and comprehension. And the same applies to programming. Yes, most students after a year of coursework have learned to program, but we all know that they are still practicing and it's still effortful, and it's still going to be years of additional practice and instruction before we stop noticing clear gains in programming fluency and comprehension. How many classes do students get on basic reading skills? How many hours of drill and skill exposure do we expect them to participate in, even after we consider them to be a reader? We start with recognizing letters, mapping them to sounds, defining words, structuring sentences, grouping sentences into paragraphs, paragraphs into essays, and there are workbooks and drill and practice expected at every step along the way. On the programming side of the coin, we generally teach an intro year and then roughly assume that you're a fluent programmer after that point. You know variables, basic control flow, functions, maybe classes. That'll do it, yeah? It does not do it. There are thousands of hours of drill and practice missing, and it shows. And even though we still publish books on learn to program in a day, dear Lord, now the subtitle is Learn to Program in a Day and Learn It Well. Yeah. We all know that this does not work, and yet it's somehow been kind of this way forever. There's a Harlan Mills quote that I find really striking. Our present programming courses are patterned along those of a course in French dictionary. In such a course, we study the dictionary and we learn the meanings of French words in English. This corresponds to learning what PL1 or Fortran statements do to data. At the completion of such a course in French dictionary, we then invite and exhort the graduates to go forth and write French poetry. Of course, the result is that some people can write French poetry and some not, but the skills that are critical to writing poetry were not learned in the course that they just took in French dictionary. This quote is almost 50 years old, and other than name-dropping PL1, it feels sadly relevant. My spicy claim, right? There is simply not enough time in an undergraduate curricula to teach programming fluency and to get significant coverage in anything else, much less the everything else that we seem to be aiming for. I am very glad that I took courses in networking and programming languages, but those were not preparing me for work in those domains. It's basic exposure to the concepts, which is great, but if it's taking time away from bigger projects and more time doing programming practice, it might be counterproductive. But the lesson for industry folks really needs to be made very, very clear. It is hugely inappropriate to assume that academia can handle all of the education and training. As an industry, it is long past time for us to recognize that paying lip service to lifelong learning is not enough. Other industries have clear goals and requirements in terms of professional development time. Doctors, teachers, lawyers, real engineers all have days and weeks of training annually in order to keep up with the pace of discovery. Software, not so much. So we're absolutely getting that wrong. Let me tell you a story about French poetry. I mean, application of programming skills. I used to regularly do phone screen interviews for Google. These are the first round, hey, just prove that you're a programmer, that we use before bringing people on site. And the stated goal is really nothing more than that. Demonstrate some level of programming fluency. So the question that I asked most of the time was just this. I will give you a number in the sense that a first grader understands what a number is. I'm giving it to you as a string. Add 1 to it and return in the same format. I had to get remarkably detailed and precise in specifying this because everyone kept trying to like, what's the trick? What are you trying to do? I'm like, there's no trick. I guarantee you there is nothing. Right. I just want you to write a little tiny bit of code, right? And then I would spend several minutes assuring people, if it seems very easy, do the very easy thing. I'm checking the basics. I can make it harder later, but knowing that you can do the easy thing is important. If there are standard library ways of doing this, start there. Solve exactly the way that you would do if you weren't in an interview. If you can do this in one line, great. As near as I could tell, about half of the new grads I interviewed couldn't write the one-line version of this. Even when I prompted them for, can this be made simpler? And can you do this in 1 or 2 lines? Certainly, some of them just really wanted to jump ahead. They sense that there's a harder version of the question coming, and I guess I can't fault them for that because indeed there is a harder version, and the harder version goes like this. Assume that the input may be 100,000 digits long. Does your solution still work? Why or why not? That suddenly touches on language depth and understanding, because in most backend or systems-y languages, this absolutely doesn't work because of overflow. Although you would be surprised at the number of people that express some uncertainty about whether a 100,000 digit long value fits in a 64-bit int. But even in a language like Python, where the one-liner does keep working, because overflow is trapped and the values in question are silently promoted to an internal representation that's like big int, adding one is kind of wasteful, right? Converting big int to string and back is clearly order n, and on 100,000 digits, that might in some cases just barely matter. Although really 100,000 is still, I forgot how to count that low in terms of modern computing. So instead, what we're really just looking for in this interview is reproduce the simplest algorithm that you learned in early math. Can you carry a 1? I suspect that this is one of the earliest things that we all learn that could be characterized as an algorithm. And sadly, that does not mean that people nail it. We get a few subtle questions in here, right? Can you loop through the input backwards? How do you convert from character to digit? And do you need to? How do you represent the carry? Are we doing multiply and divide operations throughout? What happens if you need to length extend the result? And what does that do to our, and in what cases does that occur? Is our input mutable? And if it isn't, how does that affect the algorithmic complexity? And what do we do about error checking? Because if you have managed to get the main algorithm to operate in better than linear average case, you probably don't want to spend order n time validating the input. But that comes as a surprise to most people. In my experience with this question, we get a lot of quick demonstrations that people are just lacking practice, right? They fail to run that loop backwards. They'd really like to half unroll the loop. I'll show you an example of that in a second. Explicit use of a carry when a structural invariant totally works. Multiply and divide when the entire range of the arithmetic is 0 to 10. Mixing up string versus character, which Python, I think, exacerbates, but that's a whole different rant. Mixing up the integer and ASCII domains, failing to length extend. It was not at all unusual to see answers like this. I wrote this by hand. I'm not leaking anyone's, private solutions to things. It's really hard to write this by hand this way. But you can kind of get a sense of what they're doing. The half unrolled thing is this notion like, basically that third line, the first conditional, is roughly doing the loop invariant, right? The way that they're thinking about it is like, you're going to do this once, and then if that's not done, then you do a loop, right? And there's some confusion in there. There are a lot of variable names, repeated sub-expressions, reused variables, a lot of levels of indentation, which is a smell. All of this is technically allowable, but in practice, it is a super strong signal for, this is a more novice programmer. A few hundred or a few thousand hours of practice and drill are needed both to reduce the number of lines of code needed to solve the problem and to reduce the number of bugs per line of code. But among the fluent, I have absolutely given this question to people that produced an answer like this. Or to be completely fair, we can drop the comments from this. I saw both versions. This is a perfectly correct, like very straightforward answer from a fluent programmer. And the sad part is that for a fluent programmer or an algorithmic thinker, this is very much a warm-up, right? Even when you add discussions of average algorithmic complexity, add tests, start with the one-liner version and discuss language subtlety questions. That whole sequence takes 15 to 20 minutes tops. And it was pretty common to be able to tell in about 5 minutes which path we were going to go down, the success path or the not. And one of the paths that was extremely well correlated with being unable to finish this problem in 45 minutes might be surprising: use of recursion. I was particularly surprised by the people that seemed to believe that recursion was a really important idea here. Even when prompted, I could never get a very clear answer to why they would choose recursion when a loop seems to completely suffice. And worse, no language that a candidate has chosen for this question has ever been able to solve the problem recursively. Because if we're going to recurse through 100,000 elements, any language that doesn't have guaranteed tail call elimination is going to exhaust the stack. And I've seen solutions for this in C++, Java, and Python, and up until at best the last like 2 years, none of those languages had even a mode where you had guaranteed tail call elimination. A recursive solution is slower, more confusing, and impossible to solve the problem as specified. But for some reason, about 10% of the people that were approached were reaching for recursion, at least under my anecdotal evidence. This brings up a potentially important question for us. Why are we teaching recursion? I can only think of about 2 places I've seen in the last 5-10 years where recursive algorithm was in use in my code base. And by my code base, I mean Google's C++ code base. It's 250 million lines of code with 12,000 active engineers. And in both of those 2 places, we've been spending energy to undo the use of recursion, right? I literally cannot imagine seeing recursion in a code review or a design proposal and not asking some very probing questions. It is almost always a bug in practice, or at best, it's inefficient. So I have to ask, why is this so common? Is it traditional? Is it a very good pedagogical tool for teaching a certain problem-solving approach? Is it a good tool, just my biases are wrong, it's not good in industry, like big industry, maybe? It's required by some policy or curriculum requirements. We should track those down and squish them. Or it's in the textbook. It could be any of these. I hope that we're doing it because it's a good pedagogical tool. It is a very powerful concept to lean on. Among the engineering brethren that I hang out with, we do talk about things being recursive quite a bit, like it's a very good idea. It's just not going to be implemented in code directly with a recursive solution. But I fear that we're teaching this because of tradition. We had talks just yesterday where someone was saying like, well, the faculty doesn't really want to change the way that they're doing things, right? Our discipline is too young to have traditions that matter. And honestly, recursion is not alone here, right? There are a lot of lower division topics in CS that I don't think have aged well, or that at least need some additional nuance. Here are some. Linked lists, binary search trees, regular expressions, big O, sequential computation. Really, like, y'all know threads do matter, right? That's a daily thing, not a advanced optional topic. I will dive into these a little, since I suspect that some of this is surprising. And I will start with my favorite example, linked lists. Here's a problem allegedly formulated by John Bentley back in the 90s that illustrates the issue. Generate n random integers, insert them into a sequence in sorted order. And there are 2 sequence containers that you're most likely to encounter, an array or a linked list. We can look at the theoretical average case complexity here. For a linked list, you're going to do linear search, and then it's order 1. So in practice, it's n over 2 operations, right? And for an array, you might do binary search to find the insertion point, and or you could just do linear search, and then afterwards, you're going to do an additional n over 2 work to make space. I'm going to ignore the binary search version of this for fairness. And in practice, it's therefore going to be exactly n operations. So the question is, at what size does the linked list start catching up, right? For what values of n do we expect the linked list to outperform? We're using more memory, which usually means that you get better performance, right? You have some additional cache, or you're trading off those resources. We're trading memory and CPU in order to save ourselves half of the operations, in theory. Turns out there's basically no case where the linked list version outperforms. Roughly, if we ever iterate through the sequence, ever, or do any linear probing, then the linked list is much, much worse, both in terms of memory and in terms of CPU. To be fair, there are a couple esoteric cases I can think of where it might be useful to have a linked list. In languages without reference counting, C, C++, then there may be value in having your elements have a stable position in memory, so your pointers and references point to them consistently. That could be. And in use cases where it's only an unbounded queue, right? You're going to enqueue and dequeue, but you never, ever, 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 ever iterate it. That could be okay. And that's all of the things that I can think of that generalize, right? Every other use of a linked list, I would probably question very strongly and send you some assigned reading on performance. That's basically it, right? Depending on your perspective, the underlying cause here is because of one or two deeply important points. Big O only works when your mental model for an operation is reasonably accurate, and memory caches, microcode, and optimizing compilers have all done magic on real code, real workloads, but they mean that our taught intuition is just wrong. In reality, the only thing that matters here is that the memory cache in the processor and cache locality. In the vector case, you dereference the pointer to the first element, and the processor plus your memory subsystems cache the next few entries in the vector. That dereference takes like 100 nanos, and each of the following comparisons takes a nano or less. It's nice inline stuff. Because the hardware is really good at spotting sequential access patterns, as you continue iterating through it, in general, everything is going to get prefetched and is going to be hot in L1 cache. Even when you're in the write back chunk, it's all still prefetched. It's all easy, right? This is a kind of a best case thing for what your CPU really wants to be doing. And the important point here is that pointers are either basically free, if they are cached, or hugely expensive, right? There are essays posted from the mid-90s on the oncoming wall, right? The memory wall, right? We have hit the memory wall, right? I don't know that we have talked and taught about the memory wall. The only way to reasonably assume that the target of such a pointer is pre-cached is to have recently accessed it, or if something is contiguous with it. Contiguous data structures matter. Big changes were made under the hood of the Java programming language to take better advantage of this like 10 years ago. Even if you don't have to think about memory management yourself much, contiguous allocations are still essential to having code that is at all efficient. So my back of the envelope calculations that we're going to run like 100 plus n over 3 nanos to iterate through this operation for the array or vector case. In the linked list case, we did reference the pointer to head, and then the next pointer, which is probably not cached, and then the next pointer, which is probably not cached. In all common usage, there's no reason to believe that those pointers are pointing into co-located memory blocks. Cache blocks have no chance effectively to provide a hit from one of these pointers to another. And so basically every time you chase down a pointer, it's a cache miss, right? And a cache miss these days is approximately as expensive as locking a mutex. So you get roughly 100 times n over 2. And sure, in both of those cases, that's order n. But there's a factor of 3 to 500 between these, and that really deserves to not be brushed aside. Similar arguments apply to binary search trees. First off, you probably don't need sorting. You need associativity. From high-level languages like Python dictionaries to low-level ones like C++ hash maps, one of the fundamental conceptual operations for a programmer is mapping things. I need to store some value being associated with some key. I'll look that up later. If I iterate through the elements, order may or may not matter. And statistically speaking, from having an extremely large code base, order does not matter, right? It is vanishingly rare. I think I've seen one use of a sorted container in the past 3 months. A binary search tree makes you pay the pointer chasing costs that I was just arguing about with the linked list, and the sorting costs. In practice, what you want is hashing. Hashes may have a theoretically iffy worst case performance, but that's very theoretical at this point, and may require that you talk about the weirdness that is building a hash function, although languages and librarians like myself and my team have done a much better job of making that not a problem. But hashing is really the meat and potatoes basics. Right? In general, we need contiguous sequences, array, vector, string, and unordered associative containers, and everything else in the toolbox is exotic. And even if you need sorting, a B tree is wildly better than a binary search tree, unless your objects are really weird, quite large. And in practice, the memory usage is still going to be comparable to a binary search tree. You just get much, much better locality. There's a lot of details in all of this, but it highlights a couple of things that matter a lot. Linked lists and binary search trees are cute and were probably good in the early 90s, maybe mid 90s even. But I cannot remember a single use of a linked list in code review that was justified. Caches in architecture cannot be ignored these days, right? The memory wall. I would honestly be thrilled if we spent as much time on understanding caches and memory architecture as we do on Big O. Big O is predicated on the notion that constants don't matter, but when it's a factor of several hundreds, it's really hard to trust Big O in making any sort of intuitive comparison on small scale stuff. And that is not to say that Big O is a lie, right? I would be okay with you throwing away linked lists. Don't throw away Big O. And totally happy with it being taught because it is a very useful concept, much like recursion. A lot of in practice, the places that seem most wholly good to use Big O are sort of abstract discussions. How fast is this growth? What's the fan out? And large systems where the hidden optimizations probably don't matter. Using Big O to draw conclusions between two potential implementations is iffy if you don't have a really nuanced understanding of how those implementations are going to play out in practice. And maybe the more important thing to be covered in data structures is this. Why do we use data structures? Right? In practice, by far the most important aspect of my own development as a programmer back as an undergrad was gaining an intuition for when to use an associative container, maps, dictionaries, associative arrays. Drill and practice and learning how to use such a thing well, having an instinct for, oh, that's the tool that I use for this, is, to my mind, a lot more crucial than knowing how to implement any of these things. Going back to iffy things that I have to train people to avoid, how about regular expressions? In the last few hundred code reviews I've done, I think there's been one use of regular expressions that seemed justified and not buggy. Like recursion, this is a powerful idea that is usually misapplied. And that seems really risky to give to people without some guidance and guardrails. For instance, if your regular expression language and implementation, both, aren't specifically designed with safety in mind, then in most cases, an attacker controlled an untrusted regular expression as an input is a very easy way to run a denial of service attack on your program. Perl compatible regular expressions with look behind assertions especially can be exponential time to match in very common, very easy cases. Construction of regular expression objects is really not cheap. That is a one-line thing that is hiding a lot of complexity. Any loops that involve regular expressions that are computed from some non-changing, string are super, super slow. Parsing the string, building the syntax tree, converting that to a finite automaton, those are not free or cheap operations. Simply hoisting those types of things helps. Semi-critically, you just need to minimize the number of times that a regex is constructed in any given program. The more that it's built up at program start or at first use or at compile time, the better, right? These are not the lessons that we get when we talk about regular expressions. Most simple operations, starts with, ends with, contains, are vastly more readable and faster when you don't reach for a regular expression. And that seems to be about 30% of the cases that I catch. Most complex regular expressions basically need comments and tests on their own because, wow, those things are unreadable. There's a reason that we talk about Perl jokingly as a write-only language. Still true. I don't have time to go into details on all of these things. I could probably do half an hour on the realities of multi-threaded computation. But to some extent, the details aren't critical here. It's the question, why are we teaching these? Right? Again, if it's a pedagogical instrument, that's great. That's one thing. but it's probably wise to tell the students that it's a pedagogical instrument. If it's purely for the sake of tradition, we should fix that, right? Because that argument, it's tradition, will hold for another century, and these ideas are getting comparatively worse over time. At some point, we're going to break and fix it, so we might as well do it sooner. Or it may be that my slice of the industry is not representative and you can ignore me. I don't think that's the case, but I can't prove it. I have talked to a lot of people over the years. I have moderate confidence in all of this, but without having these sorts of discussions, we'll never really find out. So I'm having the discussion. So general note, right? Pin me down here at ITiCSE. Hey, thank you, Brett, for giving me the Tuesday slot. We can have talks about this, you know, on the outing, at the banquet, on the bus, etc. I'm looking forward to it. Tell me where I'm wrong. I've been away from teaching undergrads for 15 years. It's entirely possible that I'm wildly off base on all of this. But if I'm missing something, I don't know where it is. I'll move on from things that I wish weren't taught, or were at least taught with more safeties in place, to things that I wish were taught earlier and more consistently. And for that, I have a very long list. Concurrent programming, distributed systems, teamwork, computing history, the difference between static and dynamic. I know that we talked about that in programming languages, and dear Lord, did that not really sink in, right? But that is like dominant part of my everyday experience. Like, can you reason about this statically, or do you have to run, right? Let me tell you, when you have 12,000 people and 250 million lines of code, the static, it helps. Right? I do not want to figure out how to run your code when I'm fixing your bug. I just want to be able to see it. The difference between stateless and stateful. Wow. Oh my Lord. There's so much to be said in that. Reading code, debugging skills, style, right? Have it. I saw a proposal, have a style guide approved for each language that your department uses and enforce that starting in CS1, right? Consistency. The value of consistency is on the list too. How to tell if something is just hype. There's a little bit of fashion trends going on in computing and tech. Ethics, communication, and really all of the other non-CS things that are necessary to be a good computing professional, as Brett pointed out to me earlier. I could drill down on all of this, but I don't have nearly enough time. And so instead of the long list, here is the short list. It's those. It's ethics and communication, right? And I'm sort of joking, not joking here. There are a lot of topics that I would love to see have some coverage in a CS degree. But in practice, across all of the fields that our CS grads go to, I think we would be well served with a vastly greater emphasis on this. And this shouldn't be hugely surprising, right? If you look at the march of progress in technical fields, I see some commonalities. Physics. Hey, we're unlocking the mysteries of the universe, better living through science. Oops. Nuclear proliferation and the risk of destroying human civilization. Maybe we should be careful. Chemistry, hey, better living through chemistry. We can kill bugs, get rid of unwanted hair, clean your clothes without washing them, build new materials that won't degrade for thousands of years. Oops, maybe that wasn't entirely wise either. Maybe we should be careful. Computing, hey, better living through computing and communications. I think for the last decade or so, it's been increasingly clear that computing is not an unalloyed good. If we're building tools that are going to be used by a significant fraction of humanity, small differences in equity and inclusion have outsized consequences. Social networks and filter bubbles are leading to the rise of nationalism. Con artists and scammers flourish in the crypto Web3 space. They might be the only ones there, I don't know. I, for one, would be thrilled if another generation from now, the average level of responsibility and awareness was bumped up a few notches. And I don't think that there's any group better positioned for that than you, than the undergraduate instructors. We have to instill a humanist awareness early while it still has a chance to stick. And we have to make awareness of ethics and inclusivity a natural part of the process. We cannot continue to pretend that what we're teaching here is a funny sort of applied math that exists in pure thought space, isolated from the world. The people in this room teach the practitioners that are going to shape countless systems that impact society for generations to come. I was in a panel discussion a few weeks ago making some of these points, and I got exactly the sort of questioning and skeptical response that I guessed that I would get. At what cost? What should we drop from the curriculum to make room for these soft skills? And my overly broad response is simple. I would drop everything that you have in the upper division in third and fourth year. And the reasoning for that goes all the way back to what I was describing at the beginning of the talk. Even a very good course only gives you the same time investment that you get in a month of full-time employment. If I'm hiring for compiler development or programming languages expertise, having taken a class in that is not, it certainly gives a candidate a vague idea of the flavor of the problem, but it does not give them background to rely upon. In industry, whether we admit it or not, and we're bad at admitting it, we're going to be filling those gaps no matter what. And you know what gaps I can't fill on the job? Making you a good person. Making you a responsible citizen of the world. I flat out say in team fit calls and interviews and most talks, it is at least as important to be a good person as to be a good programmer. I can make you a good or maybe even great programmer. I can only fix the other bits incrementally around the edges. Even as a systems guy, I would gladly drop all of our requirements on networking, operating systems, basically the rest of the upper division requirements. The pieces that matter most, the fundamental skills that must be seeded in academia, are programming fluency, ethical awareness, good communication skills, and a willingness to invest in lifelong learning. When we think of it as having 4 years to train up a CS practitioner, it gives a certain impression. There's a lot you could get done in 4 years. In practice, I think it might be better, at least from an industry scale perspective, to think of it as a 1.5 years of full-time work. What's the best set of skills to convey in a 1.5 years to set people on the right path, regardless of whether they go on to graduate work, big tech, startups, government, community organizing, small business, or anything in between? And I think this gets back to those lessons for industry. We have a role to play, not only in continuing education, but in situ learning. Placements, internships, co-ops, these are a hugely important part of the system. Those hands-on experiences are a critical part of integrating the classroom knowledge. Offering good summer placements for students with a wide range of experiences is a really important way to involve all of our companies in the learning process. Done well, I think arguably it could lightly influence the diversity pipeline, because a common refrain from members of underrepresented groups is that CS is too lonely, too isolating, and too off-putting in its homogeneity. Even if you haven't succeeded in building up a team with a proper representative mix, pointing out that professional work in the field is always a team effort might help. It's not as lonely as you think, right? The image of a lone coder sitting in a room late at night, this is not professional work, right? It's going to be a team of 5 going to lunch together and talking about sitcoms, right? It's a totally different thing. And although Google is not perfect, I know, shocking, we are trying to help here with scholarships, placements, and a significant internal and external focus on improving diversity. Time is limited here, right? What is most valuable? Do the tech workers that are powering your favorite charity need expertise in AI or compiler optimizations? Do the CS grads that go on to get a PhD need courses in how to do team project management? Do my colleagues in big tech actually get by with only the material presented in a databases or networks course? No, of course not even remotely. Would we be better off if graduates had more programming fluency? If we managed to incentivize them to practice and drill to compose poetry rather than study the dictionary? Absolutely, yes. Would all of these groups be better off if they were better equipped to convey complex technical problems, both to technical and non-technical audiences and stakeholders? Yes, obviously. Would humanity be better off if we spent more time training our graduates going off on these careers how to think about the moral and societal implications of their work? Yes, obviously. Would industry, especially big tech, be better off if we admitted to ourselves that we have a role to play in professional development and ongoing education? Yes, clearly. I can nitpick around the edges, linked lists, recursion. There's a lot of traditional intro, lower division material that may have outlived its usefulness. This is certainly incendiary, but I do legitimately think we could skip linked lists and binary search trees and recursion and lose very little of value. But the meat of the matter is really this. I think it's time to admit to ourselves that an intro to everything is impossible and isn't serving anyone well. We're graduating a lot of people that aren't really fluent programmers and maybe don't even know what that means. Drill would be great. Understanding that communication skills are essential would be super. Recognizing that we have the power to use, we have the potential to use our powers for good or evil, and the wisdom to know not to use our powers for evil. Yikes, that would make me happy. Right? Lifelong learning is a part of the job description. Yes, chef's kiss. They say a good talk, especially a good keynote, should be some deep thoughts and a call to action. So here's mine. Start these discussions, right? Find your friends in industry and get a second opinion. Maybe I'm completely off base. Get your industry advisory boards to sit in on the intro sequence. I dare you. See what they say. Survey your graduates and see what they actually use regularly. As a discipline, computing is not even a century old. Software engineering is just over 50. As an academic field, with not being stuck in all of those math departments, we're 30 or 40 years in, right? This is a generation or two. Doing anything at this point because of tradition is silly. But because of the growing gap between professional practitioners and CS educators, we have a lot of emphasis these days on things that aren't really relevant anymore. And I think it's time for a deeper conversation and some major reflection. And it'll start in groups like this. Let's talk and hopefully move to closing that gap. Thanks.